Welcome to Module 5, Unit 4, on histogram equalization. In this unit, we'll explore one of the most widely used techniques in image analysis. Histogram equalization is a powerful method for improving contrast, helping us reveal details in images that might otherwise remain hidden. Over the next few slides, we'll look at the concepts behind it, see how it works in practice, and compare different approaches to enhancement. Let's begin with our example image. Notice how it looks flat and lacks definition, a hallmark of a low-contrast image. The reason is clear in its histogram. This graph shows how many pixels fall at each intensity value. Here, most of the pixels are bunched in the middle, forming a tall, narrow peak. That clustering means very few true blacks and very few true whites, which directly causes the image's dull appearance. To fix this, we apply histogram equalization. The goal is to redistribute those pixel values and create a new, more balanced histogram. The theoretical ideal is a uniform distribution, where every intensity level from 0 to 255 has the same number of pixels. In that case, the histogram would be perfectly flat, like a straight line. But, in reality, this is impossible. The pixel intensities in an image reflect its actual content, the objects, textures, and lighting that were captured. We can't arbitrarily move pixels around just to force each bin to have the same count. For instance, if an image naturally has 1,000 pixels at intensity 128 and only 200 at 127, we can't simply reassign them to balance the counts without changing the image itself. Instead, histogram equalization aims for a uniform probability density. This means we remap the pixel values so that all intensity levels are more equally likely to occur. While the histogram may not become perfectly flat, it stretches across the entire range, from dark to bright, making far better use of the available spectrum. Now look at the result. On the right, the new histogram covers the full intensity range, and the enhanced image shows the difference. Contrast is stronger, details are clearer, and the overall picture looks more vibrant and lifelike. This is the power of histogram equalization. By redistributing pixel intensities to approximate a uniform distribution, we maximize contrast and reveal details that were hidden before. Before we dive deeper into histogram equalization, we first need to understand the concept of a cumulative histogram, since it plays a central role in the process. On the left, we see a regular histogram. It shows how many pixels fall into each intensity level, one bin at a time. A cumulative histogram, shown on the right, works differently. Instead of showing just the count for each bin, it adds up all the counts up to that bin. So the first bin is the same as before. The second bin is the total of bin 1 plus bin 2. The third bin adds the first three together, and so on. By the time you reach the last bin, it represents the total number of pixels in the image. This cumulative view is important because it allows us to measure how intensities build up across the entire image, and that makes it possible to remap pixel values in a systematic way during histogram equalization. In MATLAB, we can build cumulative histogram counts very easily using the function cumsum, which stands for cumulative sum. Here, the variable h represents histogram counts with 5 bins, with values of 1, 2, 3, 4, and 5. When we apply cumsum to h, MATLAB doesn't just copy those counts. It adds them up step by step. The first value stays as 1. The second becomes 1 plus 2, which equals 3. The third is 1 plus 2 plus 3, which equals 6. The fourth adds one more to reach 10. And the fifth is the total sum, 15. So the output is a new sequence of numbers, 1, 3, 6, 10, 15. This sequence represents the cumulative histogram counts. Each position tells us the total number of pixels included in all bins up to that point. As we discussed earlier, the goal of histogram equalization is to spread pixel intensities more evenly across the spectrum. In theory, the best possible outcome would be a uniform distribution, because that means every intensity level from dark to bright is used equally, maximizing contrast. On the left, you see how this looks in an ordinary histogram. A uniform distribution appears as a flat horizontal line, shown in red. In the middle, we see the same idea in a cumulative histogram. Here, the uniform distribution is represented by a straight diagonal line, shown in blue. Finally, on the right, the overlay plot puts these two together. The red flat line and the blue diagonal line are the benchmarks we compare against. The closer our equalized histogram comes to these shapes, the more effectively we are using the full intensity spectrum. Here we see another example of histogram equalization, this time with a tire image. On the left, the original gray level image has relatively low contrast. Most of the pixels are concentrated in the darker intensity range, which causes the picture to look flat and lacking detail. The histogram below confirms this, with a tall peak near the lower values and very little spread across the spectrum. After applying histogram equalization, shown on the right, the pixel values are redistributed more evenly across the full intensity range. The histogram now stretches further, and the enhanced image reveals stronger contrast. Details in the tire tread and rim that were previously muted now appear sharper and clearer. This illustrates how histogram equalization improves visibility by making better use of the available intensity levels. Let's take a closer look at what happens behind histogram equalization. In the top row, the plot on the left shows the histogram of the original image, and the plot in the middle shows its cumulative histogram. The original image itself is shown on the right. In the bottom row, we see the histogram and cumulative histogram of the enhanced image on the left and middle, with the enhanced image on the right. Now, here is how the mapping works. Step 1. Select a pixel intensity from the original histogram. Step 2. Find its cumulative frequency in the original cumulative histogram. Step 3. Take that same frequency and locate it on the cumulative histogram of the equalized image. Step 4. From that point, move down to the horizontal axis to determine the new pixel intensity. It's important to notice that the cumulative histogram of the equalized image forms a straight diagonal line. This line represents the cumulative form of a uniform distribution. By remapping pixel intensities to align with this straight line, we stretch the original histogram toward a uniform density. This is why histogram equalization works. The mapping process redistributes the pixels so the histogram becomes much closer to uniform, making full use of the available intensity range. The enhanced image shows the result: stronger contrast and more visible detail. In MATLAB, histogram equalization can be done easily using the function histeq, which stands for histogram equalization. This function automatically redistributes pixel intensities to improve the contrast in an image. Let's walk through this example. First, the command imread reads in the file tire.tif and stores it as the variable original. Next, we apply histeq to original, and the result is saved as enhanced. Then, we create a figure window. The command subplot sets up two display panels. In the first panel, we use imshow to display the original image. In the second panel, we use imshow again to display the enhanced image after equalization. This simple code shows how just one function call in MATLAB can perform histogram equalization and clearly demonstrate the improvement in image contrast. As we discussed earlier, histogram equalization usually increases the global contrast of an image, but sometimes it produces unrealistic effects, especially in photographs, by amplifying noise or making the picture look unnatural. To overcome this problem, a method called contrast-limited adaptive histogram equalization, or CLAHE, was developed. Contrast-limited adaptive histogram equalization works locally instead of globally. It divides the image into small neighborhoods, applies histogram equalization within each region, and then limits the contrast so that noise does not get over-amplified. The result is a more natural-looking enhancement. In MATLAB, this can be done using the function adapthisteq. In the code shown here, we first apply histeq to the original image, and then apply adapthisteq to produce the contrast-limited adaptive histogram equalization result. The figure displays all three versions side by side: the original image, the image after histeq, and the image after adapthisteq. This allows us to directly compare contrast-limited adaptive histogram equalization with standard histogram equalization. The figure shows the results from the example code. On the left is the original tire image. In the middle is the result after applying histogram equalization. On the right is the result using contrast-limited adaptive histogram equalization. As you can see, contrast-limited adaptive histogram equalization produces a stronger yet more natural enhancement compared to standard histogram equalization. In this unit, we explored histogram equalization as a powerful method to enhance image contrast. We saw how pixel intensities can be redistributed to approximate a uniform distribution, making better use of the full intensity range. We also learned that while global histogram equalization often improves visibility, it can sometimes introduce unwanted effects. That's why advanced techniques like contrast-limited adaptive histogram equalization were developed to enhance images locally and prevent over-amplifying noise. Together, these methods show how histogram transformations can reveal hidden details and significantly improve image quality. With just a few lines of MATLAB code, we can put these techniques into practice and see the results instantly.